We're now going to focus on generating the salx for the outer atoms, okay? And so remember that the outer atoms are our oxygen atoms, and we're going to use 2s, 2px, 2py, and 2pz orbitals as the basis set for describing these oxygen atoms. And so what we're going to do is we're going to use some group theory and perform symmetry operations on the combination of some of these atomic orbitals. And so in this case, right, we can think about if we have a carbon atom, which we are not considering the orbitals for yet, right? We're just thinking about the oxygen atoms. And then we have the nucleus for oxygen atom A and oxygen atom B, okay? Now we can describe, for instance, right, each of these oxygen atoms in terms of their 2s orbitals. So each of these has a 2s orbital, okay? And we're going to draw them as if they're in phase, okay? So in other words, right, the wave function for this, right, would be linear combination of the oxygen atom 1, O1, 2s orbital plus the atomic orbital for O2, 2s orbital, okay? And so mathematically that's what that would look like, but of course we're going to have some coefficients attached to this, which indicate that, that there's some weighting between these two for these atomic orbitals, okay? Since these are both oxygen atoms, right, there's not going to be any difference in the weighting, so in this case, right, the coefficients are going to be equal to each other, right? So mathematically that's what that looks like, but qualitatively we're going to draw this like this, right? And so what we're going to now do is we're going to perform symmetry operations that are relevant to the point group that we have decided on, or we have figured out for carbon dioxide. Now we're going to do a simplification here, where instead of doing a d infinity h, right, we're going to put in its place a d2h for the purpose of what we're about to do next. And that's important because we're going to use what's called a character table in order to determine, right, how to construct the reducible representations of this of these salx. Okay. All right. We'll redraw this over here so you can see it. So here's our 1s orbitals of our oxygen atoms. Okay. And again, we're describing this as a linear combination O1 of 2s orbitals, one for each oxygen atom. Okay. Now what we're going to do is we see in our character table on the top row, what we see is the character table name, which is the D2H, which is what we've replaced our D infinity H with for the purpose of this exercise. And then on the top row, what we see are the symmetry elements. Okay, and we're going to repeat these down here. So E, C2Z, C2Y, C2X, the inversion, sigma XZ, or sigma XY, sorry, sigma XZ, and sigma YZ. Okay. Now, from there, what we're going to do is we're going to apply these symmetry operators to what we have drawn here, our combination of atomic orbitals, our linear combination of atomic orbitals using these 2s. Okay. So first we'll start, and so remember that we changed our point group. So C2Z is really talking about this internuclear axis, right, which we had previously defined correctly as a C infinity, right? And so remember that as our Z, that's what we decided was our Z axis. So what we're saying is, what is the, in doing what we're about to do next, we're going to say, what is the result on this linear combination of atomic orbitals if we rotate on this Z-axis. And so what we see is we have this internuclear rotational axis. If we rotate it, there's no change in either the nature of the 2s atomic, of either the 2s atomic orbitals or their position, okay? So that means both of these atomic orbitals remain in the same place. And so for each atomic orbital that remains in the same place during the symmetry operation, we assign a value of 1. So we have +1 for this, and +1 for this. And so what we have then is C2Z, and then we give a value of +2, okay? I missed this symmetry operator here. So E is the identity element. And so in an identity, nothing happens, right? It remains. And so that means both of the 2s orbitals remain in the same place. So that's also 2, okay?